Alright, this is part 2 of the problem set number 2, chapter 3. Alright, part 2, beginning from question 6. This question talks about an archer shooting an arrow at a 75-meter distant target, and the bullseye of the target is at the same height. Now that's an important point. Because it's at the same height, when the arrow reaches the target, delta y is going to be 0. At what angle must the arrow be released to hit the bullseye if its initial speed is 35 meters per second? Alright, that's the angle at which it is released as a velocity. The distance is 75 meters, so once again you resolve it into the horizontal component 35 cos theta and the vertical 35 sin theta. Now the horizontal displacement is 75 meter and the vertical displacement is 0. Along the vertical, acceleration is negative 9.8 meter per second squared. Time taken we do not know. We can find the time taken using delta y is equal to v naught t plus 1/2 at squared. Substitute. Here v naught is actually v naught y because you only take the vertical component. And you know why it becomes negative, because a is negative 9.8. Okay, rearrange. Cancel out one of the t's with the square and make sin theta the subject. Now on the horizontal you can only use one equation, which is the horizontal displacement is the product of the horizontal component of the velocity and the time. So now you could make cos theta the subject from that equation. So there is your equation 1, that is your equation 2, and if you multiply the two equations, the left hand side becomes sin theta cos theta, and the right hand side takes this form. T's can be cancelled, and on putting those numbers together you get 0.3. Remember, the sin theta cos theta can be written as 2 sin theta cos theta divided by 2. Okay, what I did here is I multiplied both sides by 2, so 2 sin theta cos theta becomes 0.6. And the left hand side is a trig identity for sine 2 theta, and from which you can find 2 theta as sine inverse of 0.6. So you get 2 theta as 36.9 degrees, and theta is half of that, which is 18.4 degrees. Now in the second part, B, there is a large tree halfway between, and the branch is 3.5 meters above the release height of the arrow. Question is, will the arrow go over or under the branch? Okay. We know that at the maximum height the velocity is 0. The vertical component of the velocity is 0. So we can use this equation to make t the subject and then substitute what we know. VO is the vertical component of the initial velocity, 35 sine 18.4 degrees by negative 9.8, and you get that as 1.13 seconds. So it takes 1.13 seconds. Now we can calculate the height that it reaches at 1.13 seconds. So Once again, substituting. Remember, we're calculating the height at 1.13 because we know that's going to be the maximum height. On careful substitution and calculation, you get 6.23 meter. And now this is considerably higher than 3.50. Therefore, surely the arrow goes over the branch. That is question number 6. Takes us to question 7. Now this question is to be done as 2 parts because initially the one who is taking part in the broad jump is having an initial velocity 0 and then tries to give himself maximum velocity during a displacement of 0.600 meter. So from the initial velocity of 0, he gets a maximum velocity of something. And the acceleration is given as 1.25 times 9.8. So we can find that final velocity with which he launches himself. So we use the equation Vf squared is equal to V naught squared plus 2ay. We're looking for the final velocity with which he launches himself. Initial is 0. Acceleration is 1.25 times 9.8. And when you calculate that, you got to take the square root. Remember, you get 3.83 meter per second. Now, we are assuming that he jumps at an angle of 45 degrees because that is the angle for which you would get maximum distance on the x-axis. And we know that VOY is 3.83 sine 45. The vertical component is negative 9.8 going against gravity. Delta Y is 0. Again, yeah, starts from the ground, lands back on the ground. We're trying to find the time taken. Using the king of equations and substituting carefully, 0 is equal to 2.70 times t minus 4.9 again, t squared. Switch both sides, you get 4.9 t squared positive is equal to 2.70 t. Cancel the t and the square and find t. .553 seconds. Now, we can find the x during this time. Remember that the formula that you can use, the only formula that you can use on the x is x is equal to velocity, horizontal component of the velocity, multiplied by the time. So since you know the horizontal component to be 3.83 cos 45, we already got the time as 0.553 seconds. You get the final answer as 1.5 meter. That is question number 7. Now on to question 8. Before that, let me see. We've been talking about this, but I just wanted to show it to you again one more time. If you have a vector A, you can resolve it along the horizontal into the x component, which is A cos theta, and the y component, A sin theta, as long as the angle is taken with respect to the x-axis. And what you know about the horizontal component, it never changes. It's not affected by gravity, but the vertical component changes and is affected by the gravity. Alright, in question 8, the eagle is flying horizontally at a speed of 3 meters per second, and the fish falls into the lake 5 meters below. And what do you have to calculate the velocity of the fish related to the water when it hits the water? So what do we know about the horizontal component? That it never changes. So just before hitting the water, the horizontal component of the velocity is still going to be 3 meters per second. If it started out at 3, it's going to be 3. But the initial vertical velocity was 0. A is positive 9.8 because it's speeding up, going down. And delta y is 5 meters there. So you can find the final vertical velocity using this equation. Vf squared is equal to V naught squared plus 2a delta y. Substitute. Remember that you have Vf squared on the left hand side, so you'll have to multiply this and then take the square root of that to get 9.9 meters per second. Now, since we know that the vertical is 9.9 and the horizontal is 3, the resultant is going to be the sum of their squares and then the square root. That's what you always do when you have the x and the y components. Square them up, add them, take the square root. In this case, you get it as 10.3 meters per second. That was problem 8. Okay, now let's look at the 9th question. In the 9th question, you have a seagull flying at 9 meters per second straight into the wind. Well, the wind is going to slow it down. And the bird takes 20 minutes to travel 6 kilometers relative to the earth. And what's the velocity of the wind? Then it says if the bird turns around and flies with the wind, so the wind is going to support it, how long will it take to return? Definitely in the B part, the bird is going to take less time. Alright, so this is a simple case of relative velocity. Let not the notations trouble you. You read it as velocity of the seagull with respect to the ground. So the first letter always shows you whose velocity you are referring to. And the second one shows you compared to what. So when you say VSG, you're saying it's the velocity of the bird, the seagull, compared to the ground. Will be velocity of the seagull with respect to air plus velocity of air with respect to the ground. Okay. So to get the velocity of air, you just have to take it to the other side, becomes negative. And velocity is just displacement by time. It's given us 6 kilometers, which is 6,000 meters, divided by 20 minutes in seconds, and you get it as 5 meters per second. That is VSG. Okay, now you know. See, this is when we're using this formula actually. 5 minus 9. So that gives you negative 4 meters per second. Of course, it shows that the wind was blowing opposite to the direction in which the bird was moving. That's what this negative shows in the B part. Now it's flying with. Therefore, its VSG is VSA minus VAG. Notice the difference between the first formula there, when it was against, and when it's with. That is what you have to take care of. So now, because we know it's negative 4, there's 2 negatives, that makes a positive, and 13 meters per second, of course. The wind is helping it, so it moves faster. Therefore, how much time will it take? Displacement is velocity multiplied by time. Time is displacement divided by velocity. You get 6 times 10 to the 3 again, kilometers into meter, divided by the time, divided by the velocity, which will give you the time in seconds. 462 seconds. To get a better idea, we could change it into minutes by dividing it by 60. So that's 7 minutes 42 seconds. All right. C part. How does the wind affect the total round trip compared to what it would be with no wind? Well, wind is always going to slow you down. Although you think that in the second part, because it's helping you move faster, you may think it's going to neutralize. It never does neutralize. Wind is always going to slow you down when you take the whole round trip into consideration. Well, that is number 9, and this is question number 10 now. A ship sets sail from Rotterdam, heading due north at 7 meters per second, and that's relative to the water, see? And the local ocean current is 1.5 meters per second in a direction 40 degrees north of east. So you got to find the velocity of the ship related to the earth. You're given the velocity of the ship with respect to the water. Okay, so that's velocity of the boat with respect to the ground is equal to velocity of the boat with respect to water plus velocity of the boat. Velocity of water with respect to the ground. Okay, let me slow that down. I hope you understand that. That is given as 40 degrees, 7 meters per second is the velocity of the boat with respect to the water. Now when you look at the x components, you can write this. Just add x to that formula on top. And now you see that the x component of the boat with respect to the water was 0. Why? Because it was entirely moving along the y. Do you see the 7 meters per second is completely along the y-axis? Therefore, it has no x component. But when you take the other one, it's surely going to have an x component, which is 1.5 cos 40 degrees, which is what's going to be here, 1.5 cos 40 degrees. Okay. So this is 1.149 meter per second. You can do the same thing with the y component. Just change the subscript to y. And now it's 7 because it was completely along the y plus 1.5 sine 40. Which gives 7.964 meter per second. And since we now know the vertical and the horizontal components, you know how to find the total, square them up, add them, take the square root. That is the idea, and that is when you get the velocity of the ship relative to the earth. I hope you listening to this video gives you much more sense. All right, before I start shooting off, you see, you got to even find the angle, and that angle is called alpha. Alpha can be found using tan inverse of the y component divided by the x. Now, to give you a little bit more understanding about that, if you completed the triangle here, okay. Let me draw that again. Okay. If you completed the triangle here, then actually this is your VBGY, and this, this is VBGX. Now, therefore, it's very clear that tan of alpha is opposite side, which is this, by the adjacent side. So that is why you have that, and the numbers are 7.964 divided by 1.149. And when you take the inverse, you get 81.8 degrees, and of course it is to the north of east. Well, like I was beginning to say before, I hope this makes a lot more sense. as you continue looking at it. I know it's a considerably new topic, and all of it is coming at you, but it's all going to be easy. It's going to get better if you continue working. Thank you, and good luck.